Welcome to the Electrical and Electronic Engineering Lecture Series. The anchor person is Professor Michael Sindinechi. Today, we are continuing with our self-test in engineering lecture series. We are going to look at self-test on models 017, 018, and 022. Please follow me in the engineering lecture series by subscribing to my YouTube channel at https://youtube.com/@ndinechimichaelc. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. To learn more on this self-test, you can read up models 017, 018, and 022. Now, we are going to be asking typical questions and provide answers based on the lectures we have had in the mentioned models. The first question is, what are the main three basic elements that must be available to enable information-bearing signal to be conveyed from a source to its destination? We recall that when we were talking of electronic communications, that the basic three elements that must be there will be: one, the transmitting equipment or device which serves to couple the information-bearing signal to the communication medium. Now, the communication medium itself, which we say otherwise known as the channel, has the responsibility to transport the information to the receiver at the end user's premise. And of course, the third element is the receiver, which is the device through which the information is conveyed to the end user. The second question is, what are the important parameters of a source encoder? Now, we ask, what is this source encoder? The source encoder is that device that collects the either analog or digital information that are to be sent over from the transmitting end to the receiving end, that now converts it to the format or to the form suitable for transmission through the medium. So the important parameters of a source encoder are: one, the block size; two, the code word length; three, the average data rate; and four, the efficiency. The block size now is what is the number of bits that can be contained in one frame to be sent. The code word length is what is the number of bits that represents an information, and that for digital systems determine the number of registers or storage spaces that that system can accommodate. And of course, the average data rate is the quantity of data that can be transmitted over the encoder can transmit over a specific time. And of course, is efficiency. That is how best this encoder performs its duty. Question 3 is, what is the main objective for source coding? If you recall, when we were doing the lectures, we have channel coding and source coding. They are two different things. So now the question is, what is the main objective for source coding? Say that the main objective for source coding is to remove redundancies. Now, this redundancy in the information are those bits, if you remove them, you will still be able to convey the information unhindered. So the main objective of the source coding is to remove these redundancies in the information to be transmitted so that the bandwidth required for transmission is minimized. Take for instance, you want to send large chunk of information, and you notice that there are redundant bits that when you remove them, it will not hinder the information you're going to send. So, knowing fully well that if you send all of them, it will, they will occupy channel bandwidth. So the source coding try to remove them. For instance, if you want to, send bulk information and you zip it, by that zipping, you are removing redundant bits. Your receiver will have, the knowledge of it and try to replace those bits you have removed. So see that at the source, we remove redundant bits, whereas the main objective, question 4, the main objective of the channel coding is to now introduce redundant bits. And when these redundant bits are introduced, they help in detecting error and correcting them at the receiving end. So he said the main objective of channel coding is to introduce redundancy in the information transmitted to aid error detection and correction at the receiving end. If you look at the model 017, you will see how this was explained, that if you transmit a single zero or a single zero bit, it represents zero. If you transmit two zeros, it still represents zero. If you make it three, if you make it four, you see that instead of transmitting one bit, one zero bit, you transmitted three, which represents zero. You have introduced two redundant zero bits that are doing really nothing. They are not carrying information. But if along the transmission channel, there are distortions of, the bits due to, any interference or degradation of the signal, at the receiving end, you will still be able to recover that it is zero that is transmitted, because there is no how the degradation will occur in the 30 bits at the same time. So we say that the main objective of channel coding is to introduce redundant bits or to introduce redundancy in the information transmitted to aid detection and correction, to aid error detection and correction at the receiving end. Question 5, so list some or the advantages and disadvantages of digital communications system. So we say there are many of them, so we list as many as we can, but more importantly, that digital circuits are more reliable and cheap to realize because you make use of logic gates and logic circuits to do that. They are easy to design, they are easy to implement. Second one, signal processing functions such as compression, encryption, decimation, and interpolation can be deployed more easily. So when we will be treating digital signal processing, we will talk more on this decimation and interpolation of signals. Error detection and correction are easily employed, thereby improving system performance by reducing the probability of error occurring. 4, hardware implementation is more flexible in digital systems than analog systems because of the use of microprocessors and VLSI chips, that is very large scale integrated chips. So when you use that, you see that the analog signal or analog circuit that would have been bulky will have been reduced to just a chip to achieve similar thing. So it's a big advantage. 5, the effect of distortion, noise, and interference is less severe in digital communication systems. And 6, repeaters can be used at fixed distance along the link to identify and regenerate a pulse before it is degraded to an ambiguous state. What we are saying here is for analog systems, you can also have repeater stations, but you may not be able to regenerate the signal completely if it has degraded so much. Now, if it is a digital system, the pulse, that is the digital signal, can very easily be regenerated and you recover the exact information that is being transmitted. And 7, combining digital signals using time division multiplex in TDM is simpler than combining analog signals using frequency division multiplexing. As we go on, we will see multiplexing and questions in multiplexing and be able to explain this number 7 better. So, question 6. So, what are the functions of multiplexers and demultiplexers, encryptors and decryptor in a digital communication system? So that multiplexers and demultiplexers, otherwise known as mux, demux, can be applied thus. For multiplexers, it is used for combining signals from different sources so that they can share the same portion of the communication system, whereas the multiplexer is used for separating the different signals so that they reach their respective destination or um, destinations. So if you multiplex signals, what we are saying is that you can have signals having the different bandwidths, different frequencies, and you have only one channel to transmit them. So you multiplex them, even though they are having different frequencies, but you can transmit them down the communication channel using only one channel. At the end, the multiplexer will be able to separate those signals and send each one to its respective destination. Now, the encryptor prevents unauthorized users from understanding the messages and from injecting false messages into the system. In other words, it's a security measure. You encrypt. By encryption, you introduce some, you know, information at different points so that only the person who know where the signal or how the signal is encrypted will be able to extract it if the person is not authorized. Otherwise, the receiving end has a decryptor that reverses the encryption operation done by the encryptor. So the decryptor does the reverse operation at the receiving end so as to recover the original message using the same key of the encryptor. Now, note here that that um, manipulation you did at the encrypting end is called the key. So at the decryptor end, the decryptor will use that same key to be able to convert back the encrypted signal to its original form. So it's just a way of preventing unauthorized signal. And we say that it is easier to do this for digital systems than for analog systems. Question 7 says the representation of signals in terms of periodically taking sample values is important in communication system for three reasons. What are the reasons? See, when we represent signals periodically, we call it sampling the signal. So you say one, analog messages can be sampled, quantized, and sent in digital format. That is one of the reasons. You have your analog signal, you sample them, you take samples at different points. As we go on, we see the conditions governing the point at which you take these samples, which we call Nyquist sampling rate. So when you have done that sampling, you quantize them into different bits. When you quantize them into different bits, it becomes zeros and ones. And when you have done that, you now send it as a digital information in digital format, in form of ones and zeros. Two, it is possible to represent analog signals and systems digitally and thereby simulate communication systems on a digital computer for analysis and design purposes. See, yeah, you can simulate analog signals, but then it is very easy or easier to do using digital computers. So when you have quantized, sample quantized, and have it in digital format, it becomes very easy for you to simulate and get your result. Also, high-speed digital signal processors that make digital implementation of many communication systems possible are now available. So just a question of going to the market and picking the digital chip or digital signal processing chip you need to be able to, do what you want to do. So you see that when you represent your signals using digital bits, it makes it easy for you to implement what you want to implement. So 8 say state the sampling theory. Now, sampling theory states that a continuous signal waveform is uniquely determined by a series of uniformly spaced samples taken at a rate of at least twice as great as the highest frequency in the signal. It is very important that as a communications person, you know this. Now, if we put it in another way, a signal f of t band limited to b hertz, that is, contains no frequency higher than b hertz, can be completely determined by 2b samples per second. That is, by giving each ordinate at a series of points spaced half b seconds apart. Remember what b is. B, we said, is the highest frequency in that signal. That is why we say that it is band limited to B. Anything higher than B is not, considered or lower, but the B is the highest frequency in that signal. So if you sample at 2 times that frequency, you'll be able to recover your signal very well. Now, if you look at it, a complete circle, for you now to do that, it means that it will be sampling at half peak. So that is that. So now that sampling is done at what we call the Nyquist sampling rate, and the distance between one point you sample and the other is called the sampling interval. So now question 9 is asking us to state the Nyquist sampling rate and the Nyquist sampling interval, what we understand by that. And our answer is this: sampling at 2 times the maximum frequency, that is 2f samples per second, is termed minimum Nyquist rate. As we go on, we will see what happens if you fail to sample at this rate. So when sampling is done at intervals corresponding to the half of the peak of the sample frequency, that is at half f, it is known as the Nyquist sampling interval. So it is important to note the definition of sampling, Nyquist sampling rate and Nyquist sampling interval. Question 10 say, state the equation for the frequency spectrum, that is the Fourier transform of a typical sampled output signal. Sketch its typical frequency spectrum. Now, say when you sample a continuous signal waveform, you get it as a function of time. Then you use your Fourier transform to transform it into its frequency component. That is using the omega terminology. When you do that, you have your Fourier transform of that signal, and it is usually as given in the equation: S of omega equals the f omega plus the summation from minus infinity to infinity, where n is not equal to 0, then sine pi nd over n pi nd f of omega minus n omega c where omega c is the carrier frequency. So if you now put that into your oscilloscope, for instance, that signal, what you will see is like the figure we have seen. You see the Fs of omega at the center O. So to the right and left of it, you see the first harmonic of the signal ranging from 0 to minus B on the left and 0 to plus B on the right. So if you go further another distance from that 0, you have the harmonic of that first signal, which we give to the left Fc minus B, where Fc is the current. And the signal continues to decrease amplitude by the rate giving us sine pi nd over pi nd, which is called the sync formula. So now the importance of this is that you have harmonics decreasing in amplitude. Each of the harmonic carries the same information, like when we did our modulation. So the important thing now is to extract this information. Let's go further to see what happens. Now, question 11 says, what are the effects of sampling outside the Nyquist rate? Now, that figure we've just seen, that's what we repeated here, but this time around we used two colors, the blue and the purple color, to be able to explain what is happening. Now it says sampling outside the Nyquist rate could mean sampling at a rate higher than the Nyquist rate or sampling at a lower rate. Sampling at a rate lower than the Nyquist rate will make the frequency of the carrier and all the harmonics to start closing in on one another, and eventually all the spectral components will overlap and match. Now, let us picture what this sampling means. If you stay in your house looking out through the door and people are passing, you see, if people are passing at a constant rate, then you don't have to continue to be looking at the door to know the number of people that have passed. So if they are passing at the rate of one person per every 2 minutes, so you see, you need to now look at the door every 2 minutes and see the person pass. After that, you can be watching your TV. In the next 2 minutes, you look at the door and see another person pass. Now, when you are doing that, you are doing it at the Nyquist rate at 2 times the frequency. But if you now do it after 3 minutes, you now see that you will not be able to get the number of people that are passing through the door. Now, we're saying if we apply that to our communications, that signal we saw up, let's go up a bit. That signal we saw up, you can see how the two that centered at 0 is one starts from zero, the other one ends in zero. So there is a clear-cut demarcation where two of them, meet. So they are not overlapping. But we say if you now sample at a rate lower than this Nyquist rate, you can now see how the signals at center zero, the purple and the blue are overlapping. So as you continue to sample at a rate far lower than the Nyquist, they will continue to overlap more and more. So now, again, if we sample at a rate greater than the Nyquist rate, then we will have so many information that it will take us a large digital file to accommodate. So now, what happens is that if we sample at that rate lower than the Nyquist rate, it becomes difficult for us to filter out, because if you are filtering the signal in purple, a portion of the one in blue will enter. If you sample at exactly 2B, that is the Nyquist rate, you will now have to have a filter that will be, an ideal filter to be able to get from zero to B in that signal. Let's look at it again. Take, for instance, the center one that is at zero. To the left, we have minus B. To the right, we have B. We are saying that that is what happens when you sample at Nyquist rate. Now, for you to get the one or the signal from zero to B using your filter, you must have a filter that is a pure rectangular wave filter. And we say that that filter, which we call the ideal filter, is not a practical filter. In other words, it doesn't exist, or you cannot get it in real life. So when you don't get it and you have a filter that is spreading, at the base a bit, you can see that there is no how it will end in zero. Now, let's see again. So we now say that the best way to take care of that is to make sure that there is a small gap between when this signal ends and when the other signal begins, so that when we have practical filters, we will be able to recover this signal. So now that overlapping has a name called aliasing. So you say, what is aliasing? Say, this is the phenomenon of overlapping as described in question 11. That is, when the two signals overlap, we call it aliasing. It has an effect which, if we have time, we explain. In any communication where you have, signals overlapping, you have things like shadow and, other things. So this overlapping, which you have described in question 11, is known as aliasing. And the distortion that results is what we call it. Aliasing occurs when a signal is discretely sampled at a rate that is insufficient to capture the changes in electrical signals. That is, when we sample at a rate less than the Nyquist rate, which is 2B. Aliasing occurs. Now, so how do we recover sample signal, and what is the difficulty associated with recovering a sample signal? And how can this difficulty be avoided? Now, we recap quickly that when we are advised to sample at 2B, that is the Nyquist rate. So when we sample at a rate lower than that Nyquist rate, the signals start overlapping. When we sample at a rate far higher than the Nyquist rate, we have so many samples or so many results, which will now require us to have a big storage device to be able to capture all of them. Now, how do we now best recover these sample signals? We say that the simplest way to recover the sample signal is to pass it through a low pass filter of bandwidth Bhertz, where Bhertz is the maximum frequency of operation. Now, this is as illustrated. Now, let's take this signal to be, you see, signals here, to be the sample signals as we have seen in the figure above. Now, if you look at the dotted line, which is, like a pulse, that is a filter. And of course, we know what a filter is. It allows certain range of frequencies to pass. So, we are saying that this filter, under normal circumstances, which is sampling at the Nyquist rate, must have a sharp cutoff characteristics to be able to capture the signal. If you look at it, you see that dotted line, which is, the filter age, comes exactly when this signal ends and that other signal begins. But because we said that only ideal filters can do that, that practical filters cannot do that, you can see that practical filters will always spread at the base. Let's see it. You can see the filter characteristic required, that is, that dotted line at the base must spread. And if you allow the two signals to, come and end by sampling at 2B, you see when the base of that filter, expands, it will capture a bit of the signal on the right. So our question is, how do we recover this? So for us to recover this, we do something. And that something is to sample at a rate a little higher than the Nyquist rate. Remember, it says when you sample at the Nyquist rate, you will recover the signal fine. But practically, you will not be able to do that because practical filters cannot do that. So we say that for us to recover very well, we sample at a rate a little higher than the Nyquist rate. So you say the difficulty associated with this is that the filter required must have an infinite cutoff characteristics. That is, must be an ideal filter in order to avoid overlapping of the recovered samples. This difficulty can be ameliorated by sampling at a rate slightly higher than the Nyquist rate, so that the output will create a little gap between the successive samples as shown below, and then use practical filters to recover the samples. This gap between successive samples is known as the guard band. So you can see now, if you sample at a rate a little higher than the Nyquist rate, you can now see gaps will be created between one signal and the other, or one sample output and the other sample output. So when that gap exists, we call that gap the guard band. Now you can now see how that filter spread, that is the filter in the dotted line, spread down. But even though it spread down, it did not cut or into the signal on the right of it. So you see, with that, you overcome the problem of not being able to use practical filters to do to recover your signals. So the signal on the right will not overlap slightly anywhere. So now, depending on how good your filter is, it may not spread so much, so you will be able to reduce the size of the gap band. Some places it's called the gap band, but the correct term is the guard band, that guards your signal from overlapping with the other one. So, thank you for going through the self-test with us in the engineering lecture series. Don't want it to be very, lengthy. Maybe in the next 2 days, we also do for model 22, 26, and 28, so that we made it short to help you go through easily and understand what is being said. So maybe in the next 2 days, another set of this self-test will come to cover our area of communications in the engineering lecture series. Before we go, I want to, put this across to you, that a bird in hand is still worth less than the other 20 in the bush. Enter the bush and hunt for more. What comes to mind here is the saying that a bird in hand is worth more than so many in the bush. I said, if you enter the bush with the technique with which you caught the one you have, you will be able to catch more birds, because there are many of them in the bush. In other words, we are saying that you should not strive for less. Always go for more. And by going for more is to strive to study harder and harder, so that you gain more knowledge. Thank you for being with us in the lecture series.